So here we go. So yesterday we had a theorem, so you can all see me writing, hopefully. If not, let me know. Um, and instead of doing a chat, I would just go ahead and, just put your mic on and ask a question, or you can leave it on is fine too, because I kind of prefer that a little bit. But yesterday we had the triple scalar product. So if you remember, we said that A vector cross B vector dot C vector is equal to A vector dot B vector cross C vector. So this is really pretty easy to remember. We proved it yesterday with a little help from Jordan fixing a few things and Isaac fixing a few things I did. But anyway, so we proved that yesterday, but this is the triple scalar product. All we're really doing is switching the cross product and the dot product where they're at. And then now I wanted to jump to the, in the book, Jordan asked, where are we ever going to use that? Well, the book, they just had three vectors, A vector, B vector, and C vector, and said, show that the triple scalar product is true, which is going to be true no matter what those three-dimensional vectors are, right? But anyway, then we have the triple vector product. So this is triple scalar. This one is so I'm going to call it triple scalar product, TSP. This is going to be the triple vector product, TVP. All right. So anyway, so this says that A vector cross the quantity B vector cross C vector. Okay, now here I do need parentheses. On the triple scalar, I didn't because I have to do the cross product first, right? I got to do that first. Otherwise, you have a scalar and you can't take the cross product. So down on this one, I am going to need parentheses there. And then basically what I do, kind of in the old distributive law, we would take that A vector and kind of carry it through. But this is a little bit different. This is going to be A vector dot C vector, which is a scalar, right? And then, so a scalar times B vector, and then minus A vector dot B vector times C vector. Okay, so this is, we got to be careful what this is. So I do want you to notice, do you see any cross product on the right side?
No.
No, right? So there's no cross product on the right side. So it doesn't look, the right side doesn't look anything like the left side. Okay, so we got to be a little bit careful with that. What we have is A vector dot C vector is a scalar, and so is A vector dot B vector. That's a scalar, right? And so really what we have is scalar multiplication times B vector, and then of course we have a minus sign in here and stuff too. So, but anyway, so we got scalar multiplication on the right side and then a difference of those two things. All right, so it takes a little bit of getting used to there. So there's no, I used to draw a circle around the A and connect it to the B and C. We can't really do that here. What we have to do is we have to do the dot product with the C first, and then times B vector, and then we have to do the dot product with the B next, and then times C vector. So I don't know. That is just, I don't know how you want to do that. But anyway, this is the theorem, and that's the triple vector product. Okay, they do leave that as a proof, number 42. Do you know if I told you to do that? I didn't, did I?
No, you didn't.
Why? Okay. I don't know if I want to waste time or not waste time. I don't know if I want to take time doing that. Let's just look at a couple examples here. Let's see, clear annotations. So instead of doing that, let's just move on, and let's just show it for an example. So let's look at A vector equals 1, 2, 3. B vector equals 0, -4, 2, and C vector equals -3, 0, 1. Okay, so if I do that, basically, if I do A vector cross B vector cross C vector, let's see. How about what is B vector cross C vector? So this is going to be A vector cross B vector cross C vector. Let's do this one in red. Okay, so B vector cross C vector. Remember, like if I have my, I can kind of do this up here and then just do, that's IJK, right? And so if we do that, cover the I up, it's -4 minus 0, right? Times I hat. So it's -4 I hat, or I'm just going to keep it as a vector, -4 I hat, and then the middle one, so it's going to be minus, and then it's going to be 0 minus a -6, which is 6. So minus the 6, because it's minus that thing times j hat. So let me just double check this. I'm going to mute that, hopefully. Well, I can't mute that phone. Can't mute all my phones. All right. But anyway, what did we say? This is -6. Is that true? Do you agree? And the k hat 0 minus 12 is -12 plus a -12 k hat. All right, sorry. Anyway, now I'm going to take A vector dot that, okay? Or I mean cross that, cross this one. And what am I going to get on the left? I'll put my answer in blue. But I'm going to get a vector, right? So if I cover up the 1 and the -4, it's going to be -24 minus 18. So plus 18 is -6, right? So hopefully I'm doing this right. If you disagree, let me know. And then we got to subtract when I cover up the middle one, and it's going to be -12 minus a -12. So that works out. So 0. And then the last one, if I cover up the end, it's going to be 0 minus a -6 is +6. So I believe that the left side would be -606 if I did it right, which I'm hoping, because I did not do this example. I just made this up right now. All right, so let's do the right side. The right side is going to be, what do we have? We have A vector dot C vector times B vector, and then minus A vector dot B vector times C vector, scalar multiplication. So let's do those dot products first. A vector dot C vector, Jordan do that one, Isaac do A vector dot B vector. Isn't that 0? No.
A vector dot B vector equals 2.
Zero minus 2. Wait a minute.
A vector dot C vector is 0.
See, that's what I thought. So how's that work out? So it's -3 plus 0 plus 3. Okay, well, that's fine. So that's what I got, Jordan. Let me do A vector dot B vector. So 0 plus -8 plus 6. Isn't it -2, Isaac? Am I doing that right? 6, and that's -8, right?
What?
I believe that's
B dot C, B vector dot C vector?
No, you're doing A vector dot B vector.
Oh, duh. I'm sorry. Yes, yeah, you're right. It would be -2. Yep. Yeah, I did the wrong one.
So I'm gonna put under. I'm trying to use. So it's 0 times B vector, which is 0, and then minus minus 2 times c vector. Well, this is just going to be 0, right? Right? Actually 0 vector. So it's 0 vector minus, is going to be 0 to each component, and then plus 2 times c vector. This thing, it keeps moving the size of my screen. You can't see my screen getting bigger and smaller, can you? But it's doing it for me. So 0 vector plus it. So basically, if you add the 0 vector to a 3-dimensional vector, it's like it didn't happen. So it's 2 times c vector, right? So what's 2 times c vector is 2 times negative 3, 0, 1. And that ends up being, hopefully, what we have here, negative 6, 0. What? I get 2, don't I? So we better check and make sure we did the left side right. That's not what I got on the right side, is it? I just want to making sure so that let's go back to the right side. Did I do b vector cross c vector correct? It'd be minus 4 minus 0 is minus 4i, and then minus 0 minus a minus 6. So it'd be minus 6, a positive 6, which is minus 6, and then plus 0 minus, oh, that's where I went. No, wait a minute. I'm crossing the last one out. 0 minus 12 is minus 12. So B cross C looks right to me. Do you agree? And then I did, so basically I'm checking the purple step. Now I'm going to have 1, 2, 3 cross minus 4, minus 6, 12. I'm just going to do this. I'm just going to do this where it's easier to see. So IJK.
Wait, how?
What?
Yeah, I'm getting negative 6, 0, 2
For the purple part?
Correct, yeah.
Okay. Well, probably. I mean, hopefully, because otherwise, so I'm A cross this, so minus 4, minus 6, 12. If I cover the first one up, I get minus 24 minus a minus 18 is minus 6. That's correct. And then minus, cover the middle one up, minus 12 minus a minus 12 is the opposite of 0, which is 0. And then cover the last one up. This is probably where I messed up. So minus 6 minus a minus 8 is plus 2. Okay, well, you guys didn't catch me on that. I was trying to do that in my head, but I was kind of looking at this purple, and my eyes got a little confused. So the good news is these are the same, right? So that was it. It was just a clerical issue, which they should be the same because it's a proven fact. It is a theorem. Number 42 proves this. Okay. Any question on that? Hopefully not. So let's move on. Whoa. I just lost my writing utensil. That wouldn't be good. And then now we have another theorem, which is a follow-up theorem called a corollary. I'm on page 20 in your notes. If we have two non-zero vectors with the same initial point, then so let A vector, B vector, neither one of them are equal to 0 vector, okay? And then with same initial point. And this is, I think, some of the stuff that Isaac was talking about. Here's A vector, here's B vector. Okay, so I got the same initial point there. Then basically, if we form a parallelogram, so if I come up here and do another version of B vector up here, another representation of A vector here, and kind of connect them, that ends up being a parallelogram. So the area of the parallelogram is equal to the norm of A vector cross B vector. So this is a nice physical application of cross product on there. Now, the how would we prove that? So I do have the proof of this in your notes as well. But what is area? Let's just say, what's area of a parallelogram? It's base times height, right? Isn't it? So there's my height. The question is, what's that height there? Well, if this the angle in between has sine theta, or excuse me, is theta, could I figure out this is a 90-degree rectangle, right? So the sine is the opposite, sine of this is the opposite, h, over the hypotenuse. So what is the distance of the hypotenuse? What's the distance of A, or how long is A vector?
Norm of A vector?
Yeah, it's just the norm of A vector. Same, now I don't know how long this piece here is, right? Because it's part of the norm of B vector, it's only a portion of it, but I don't really need it, because what I can say is I could say that the sine of theta equals opposite, which is h, over the norm of A vector. Now, we also had a previous theorem, if you remember the previous theorem, that said, well, I don't know if I gave that theorem to you yet. I didn't give you that. I didn't give you a cross product theorem. I think that's next. Huh. So anyway, the question is, what is, I apologize, I gave my assistant the day off. So I can't help that. There is a chance that if somebody calls that I really need to take the call, I'm going to take it. But all right, so here we need another theorem though, right? So anyway.
Thank you for calling Ryle Financial Team.
Stop it.
When leaving your message, please do not leave buy-sell orders as we can't guarantee.
All right. Anyway, we need another theorem. So we have another theorem that says we need to relate the norm of A cross B. And we have this. It's just amazing. Like they can't get me at my office, so they call my cell phone. Like, just leave a message. Maybe call my cell phone later. I think we need the. Do we have anything that relates norm of A, norm of B, sine theta? That was cosine theta, wasn't it, in a previous section? Like A dot B. Then we have. You remember that theorem? That would have been in 10.3, right, for dot product?
Yeah, it's like A dot B over like the norm of AB or something like that.
And what does that
Or-
equal? Does that equal let's see if I can find it quick. It's cosine, it uses cosine theta. And so it's, yeah, scalar projections. It's A vector dot B vector is norm of A, norm of B cosine theta, which I don't know what cosine theta is, right? Because we don't know how far that distance is. I suppose we could figure it out using Pythagorean's theorem, couldn't we? I don't really want to. But we could figure out if I called this little b for the portion of the length, you know, then b squared plus h squared equals the norm of a quantity squared. But I'm not gonna do that. I want to use this somehow. So I'm gonna clear the screen because I'm out of room here. So we need another theorem. I didn't realize we needed this theorem first, but I do now. So here's another theorem that we have, and this is on page 878. But it says that the norm of a vector cross b vector, the norm of a vector cross b vector is going to be the norm of a vector times the norm of b vector sine theta. Okay, so that is kind of nice, and angle theta is the angle in between. So anyway, and then what was the theorem that we're trying to come up with? We're trying to come up, we had our picture here. Well, we had this. And we called that h, that's theta, right? This is the norm of a vector, right? So we have the sine of theta, we said is h over the norm of a, right? Opposite over hypotenuse, norm of a vector. And then, so instead of sine theta, we can do this, and then what happens to the a vectors? Those cancel out as well, right? And then, so what do we have? We've got the norm of a vector cross b vector equals the norm of b vector times h, right? Well, what's the norm of b vector? This was, remember, this was b vector, so what's that distance? The distance is the norm of b vector. And what is area of this parallelogram? It's the base times the height. The base is norm of b vector, so that's the base, and h is the height right there. So anyway, so what does that equal? By this theorem, it equals the norm of a vector cross b vector, right? So what did we say on the previous corollary? What was that theorem on the previous page? Basically that the norm of a vector cross b vector is going to be the area of the parallelogram if they start at the same point. Okay, so that's kind of nice for non-zero vectors. So we used a, I think I got ahead of myself in my notes, because in my notes I hadn't given you that theorem yet. Maybe I didn't give you did I give you that theorem on the, I didn't finish it. I skipped a page. So I was supposed to give you this theorem first. This is on page 19 and a half. I just thought I was done with that page. I skipped over it. Anyway, but a cross b, norm of a cross b is norm of a, norm of b sine theta. And we can use that to prove the area of a parallelepiped. Okay, so let's clear that. And then we also have a couple of things. So gotta get this. How do you know a vector is perpendicular to b vector? If and only if what?
They're orthogonal.
Well,
A
right.
dot b equals 0.
The dot product equals 0, right? And that 0 is a constant, right? Now we have another result. A vector is parallel to b vector if and only if the cross product equals 0 vector. Okay, so these are two nice results that we have. So if the cross product is 0, now remember what does the cross product, if I just have a vector and b vector, what does the cross product do? The cross product gives you a perpendicular vector, right, to both of these, right? So it gives you a vector that's perpendicular or going to be normal to both those. However, but if A is perpendicular to, not perpendicular, parallel, if A vector is here and B vector, I'll use a different color, is here, and they're parallel to each other, and let's just start them at the same point. So I'm going to bring my B vector down here, can I? So there's B vector, so I can shift the position. If I take the cross product of those, basically, well, I don't know if I'm saying this right. Could I come up with one as perpendicular? I can, right? But anyway, they're going to be parallel if the cross product is 0 vector. So the cross product gives is there a perpendicular vector to both of them? There should be. So I don't know. I don't know if I'm following that. So I got to go back and read that. All right, but anyway, so we have a couple of results to know on parallel and perpendicular vectors. All right, and then with that, just kind of to summarize another thing, this is bottom of page 19 and a half, but theorem 12, if A and B are vectors in 3 space, then the cross product is perpendicular to both A vector and B vector, which we already knew that. So we had already covered that. All right, let's just look at an example. Let's do number 19. Have you done 19 yet? Maybe you have, since I've been telling you to do this stuff, but I was working ahead if you did.
I haven't.
Okay, well, let's do it. This is number 19, section 10.5. It says find the area of a triangle. So we want the area of a triangle with vertices given by 0, 2, 2. So it's connected by these points, 8, 8, 2, and, excuse me, 8, 8 minus 2, and 9, 12, 6. Excuse me, that's, yeah, 6. Okay, so basically this is going to make a triangle in space, right? 3 points in space, you connect the dots, you get a triangle, right? Well, the reality is, so I'm gonna kind of draw it at an angle. But let's say this is it. Really, what I need to do is I need to make a vector. Because what do we know? Area of a triangle is going to be half of the area of the parallelogram, right? Isn't it? So I could, do this. Sorry, I went a little long up here. But anyway, that's a parallelogram, and this would be area 2, this would be area 1. I'm looking for area 1, right? But the area of the parallelogram is area 1 plus area 2, right? So I think that would be it. So really, if I have the same initial point, and let's just say, I don't care which one I use. Let's say that initial point, I'm going to use a different color here. Let's say the initial point I'm using for both of this is here. So let's use this for our initial point. You can use any one you want. So if you want to go back and rework this, make sure it works out. Anyway, this is going to be A vector. This is going to be B vector, but A vector, I'm going to use these two for A vector, and then I'm going to use these two for B vector. So I got to come up with that. So Jordan come up with A vector, and Isaac come up with B vector. Remember how to do that? Anyone? Don't you do just ending minus beginning?
Yeah, that's all it is, right? So for A vector, it would be -8, -6, 4, I believe, right?
Yep, because just top one minus the bottom one. And for B vector,
It would be 1, 4, 8.
yep. Okay. And then, of course, what does our theorem say? The area of the parallelogram is in red, so that's all of it. And what is the area of the parallelogram? It'd be the norm of A vector cross B vector, right? And then I'm going to want half of that for area 1. But the norm of A vector cross B vector would be the norm of the cross product. So let's see if we can do this right. So if we cover up the first ones, it's minus 48 minus 16 is minus 64. Just tell me if you see me doing something wrong. Cover up the middle ones. It's going to be, I'm going to put my minus there so I don't forget it because I was forgetting it yesterday. But minus 64 minus 4 is minus 68. So that ends up being a plus of 68, right? And then cover up the last ones, and it's going to be minus 32 minus a minus 6. So minus 32 plus 6 is minus 20. What I say? Minus 32. My screen just moved. Minus 32 plus 6, minus 26. Is that right? Hopefully. And then what do I got to do? What's the norm? So it's the norm of this, right? Which is the square root of those things squared, I believe. 64 squared plus minus 64 squared, but the minus signs don't matter. And then plus 26 squared. So this would be, the norm of that would be the square root of 676. Right, everybody see what I do? Because it's square root of minus 64 squared, etc. plus dot, dot, dot. Anyway, so it's square root of 676 if I'm doing my math correct. And is there a perfect square that lives in there? Well, 676 divided by 2 is what? 676 divided by 2. The hell am I? I'm not getting the right answer. What are we doing
Yeah.
wrong here?
There's a, oh.
Did I do something wrong?
Oh, not that I know of. I was just saying there's a perfect square in there.
What is it?
Well, it's 26. Yeah, it's 26.
26 squared?
Well, yeah.
Huh. Well, is that what the back of the book says? So it'd be 13, wouldn't it? You know, if we did half.
Yeah.
That's not what I got the last time I worked this out. It's 9 square root of 29.
Yeah.
What the heck are we doing wrong? I just have the answer in my notes. I got an example up above. But then, do you guys see example at the bottom of page 20? Do you see my example number 19? Minus 8, minus 6, 4, and then 1, 4, 8, ending minus beginning. Using that as the initial point. And I got to take the cross product. Did we do the cross product right? Minus 48, minus 16. Isn't that minus 64? I, and then minus 64, minus 4, minus 68, and then plus, so it's minus that.
Should be right.
And then minus 32 minus 6. Let me do that one again. That's minus 32 minus a minus 6. Minus 32 plus 6 is minus 26. Did I do that right on my calculator when I squared them out? 64 squared. That's not, is 4,096 plus 68 squared is 4,624. Oh, I'm not even close. Plus 26 squared. I screwed this step up. The last one, 26 squared minus 26 squared is the 676, right? So I was just looking at my calculator wrong. So this is minus 64. The norm of this, good gravy, is minus 64 quantity squared plus 68 squared plus minus 26 squared, which is the square root of 9,396. So you guys, yeah, I'm going to say 676 for the sum of the squares of these things. All right, I'm going to clear this so you can see it better. But anyway, so the norm of A vector cross B vector is the area of the parallelepiped, and it's the square root of 9,396. So I wasn't done. But now we got to try and find the biggest perfect square that lives in that. Do you know how to do that? I want to prime factor this, right? So is that divisible by 16? It's divisible by 2, but it's going to be divisible by 2 again. So 4 is a perfect square that lives in there, but I could maybe divide it by 16. That doesn't work. So anyway, but it is divisible by 4. 96 divided by 4 is 2349. Okay, so 4 is a perfect square that lives in there, right? Because it's 2 times 2. Sorry, I don't want that 4 circled, but anyway, what about 2349? Is that prime? Well, it's not divisible by 3. 5 plus 4 is not, it is divisible by 3. Let's see if it's divisible by 9. It is. It's divisible by 9, and that's 261. Do you know the divisibility by 3 test? Add them up if it's divisible by 3. Anyway, this is 3 times 3. So we got another perfect square that lives in there. And then 261 is prime. You can check all the primes less than or equal to the square root of it. Square root of that is 16. So I can check the primes leading up to less than or equal to the square root of 261, which is 16 point something. 16 is not prime, neither is 15. But I've already checked 2, 3. It's not divisible by 5. It's not divisible by 7. It's not divisible by 11. And it's not divisible by 13. So basically, this one is prime. No, it's not. It can't be if I get that answer. 29, 261. Maybe it is divisible by 7. Nope.
It's divisible by 9.
It's divisible by 9 again.
Yeah.
I didn't check 3. Oh my gosh. 8, 3, or 2 plus 6 plus 1 is divisible by 3. It's actually divisible by 3 again. All right. So this is 3 times 3 times 29.
Yeah.
So anyway, my theory worked, but I just skipped the first one. All right. Anyway, so what do we get? So this is square root of 2 squared times 9 squared times 29, right? Which is, I can bring the square root of these two out, and it's 2 times 9, which is 18 times square root of 29. That was the area of the whole thing, right? So the area of the triangle is half of that. Nine root 29, which is what the back of the book had. So Good gravy. All right. That work? All good on that?
Yep.
And okay.
Yep.
So I have another example spelled out in your notes. It's different ones. So I just did 19 for you too. But anyway, so there's a different one spelled out in the notes. If you wanted to practice one, you could try that one on your own. Make sure you get my answer. What else do you need to know? So another example, and I'm on page 20 and a half. It says example, I've got 3 points, and that gives a plane, and you want a unit vector whose representations are perpendicular to the plane through PQR. Okay, so I'm just gonna draw this out. You've got this on here, but basically I've got 3 points. Again, it kind of makes a triangle, huh? What's that? But anyway, we can have a plane through those. We can keep this going, right? So we can have a plane through these points. All right, so that makes a plane. And then what I want is I want representation of normal vectors that are perpendicular to this plane. Well, what we can do is same deal. We can just pick a point, and we know that the cross product of the blue ones. So if this is a vector, if we consider this a vector and this a vector, then the cross product is going to be perpendicular, and then we can just have a unit vector representing that. So that's what I did. So we just did P be the starting point, and so we did a vector for PQ, and we did a vector for PR, just like we did in the last problem, and we got those. And then we took the cross product, and then that gives me the red vector. So the red vector, if you're looking at your notes, is 14i minus 14j. So if I call that sorry, I thought that was red. If I call that n vector in your notes is 14i minus 14j. So it's this. If I want a unit vector in that direction, then it's the n vector divided by the norm of n vector, right? So it'd be 14i minus 14j divided by the square root of 14 squared plus minus 14 squared, which is going to have a 2. That's 14 squared is 196, isn't it? What's 14 squared? 196. So it's 2 times 196. So anyway, this ends up being 14 times the square root of 2 on the bottom. And then I could do each part divided by that. So u vector is going to equal I vector minus j vector divided by the square root of 2 is one way to write that. Or we could simply write it as 1 over the square root of 2 for each one. 1 over the square root of 2, and then minus 1 over the square root of 2 for I and j vector, for a unit vector. And then, of course, I rationalized it as well on there. All right. The last example on page 20 and a half, got 3 points. Find the equation of a plane. What's the equation of the plane? This goes into the top of page 21. So I need to kind of get going here, but I just want to give you enough going on there. So we have the equation of the plane on the top of page 221. We have a normal vector to the plane is vector ABC, right? Sorry, you follow, do you both have my notes that you can see? Or not?
Yeah.
Yeah.
Isaac? Okay, so top of page 21. We got that equation of plane. A normal vector is gonna have is vector ABC, right? So we can come up with a normal vector. That's why I kept calling it N instead of A cross B. So the reality is when we have A vector and B vector, I was calling the perpendicular vector here. I've been calling it N vector, but one of the N vectors could be A vector cross B vector, right? So that's really what I was doing. I was calling it N vector, but really it's A vector cross B vector because there's a lot of N vectors, right? Here's to the plane, to the blue plane. Like if we made a plane here, this is also a normal vector here, right? But it's just a different representation of like this is N1, that'd be N2. But A vector cross B vector is one of the perpendicular representations to the plane. Anyway, so then we can use that and then just use one of the points. So we take A vector cross B vector, we get that, we plug in one of the points for the normal vector, and then we're good. And then you got your equation of the plane. So really that's a pretty simple process. Are you following that, or do you want me to do a different one?
No, I think I'm good.
Jordan?
I think I'm good too.
Okay, because those are some of the things that you're going to need to do. And then next example, it says find an equation of a plane through 1, 2, 3 perpendicular to two other planes. Well, if I'm perpendicular to two other planes, then so P1 and P2 is plane 1 and plane 2. Then the normal vector of the plane I'm looking for, when I take the dot product, I get zeros, right? So I got two dot products that are going to give me 0. And of course, the normal vector of the plane I'm looking for is vector ABC, right? And I have the normal vector for the two given planes. So the first plane, plane 1, a normal vector for that plane is vector 2, 1, 1, 2, 1, minus 1, reading the coefficients. And for the second one, it's 1, -2, -2, reading those coefficients. And then I'm looking for a plane that's perpendicular to both. So the normal vector for that plane is ABC. Take that dot product, we get 2 equations and 3 unknowns, right? And then what we can do is work our little magic that we did, either with Gaussian elimination or some other stuff, and represent everything in terms of A, and then we can divide through by the A, and that's goes through the middle of page 21.5. The other thing, so that was kind of the way we had done it before, but the other thing that I'm showing here is that you could come up with a new normal vector, because if you take the cross product of the normal vector for the first plane and the normal vector for the second plane, you're going to come up with a vector that is perpendicular to both of those vectors, right? Because that's the definition of what a cross product does. So this is the easier way to do this. Now that we have cross product, would just be to take the cross product of N1 vector and N2 vector, and that gives me a new vector, which is -4i plus 3j minus 5k, and therefore the n vector that works is -4, 3, -5 vector, and then I can just plug that in for my ABC, which is equivalent to what I got up above, right? Except that it's multiplied through by -1 up above. So, but it's equivalent. So the bottom way of doing that is so much easier than trying to use 2 equations and 3 unknowns, right? Let me draw that and pick, you seem confused. Here's a plane, okay? Here's another plane. and they intersect each other, okay? I'm going to say they intersect each other right there, all right? And then I want to come up with a third plane that's perpendicular to both, okay? So I want this to be perpendicular to both those other planes. And so the vector, the normal vector for the purple one is going to be perpendicular to both the other vectors, the other normal vector, the normal vector for the first plane and the normal vector for the second plane, right? But what I can do is for this one, I can let this be given by the first normal vector cross the second normal vector, because this is going to be perpendicular to both this one and this one, because the cross product of these two is perpendicular to N1 and is perpendicular to N2, right? So let's see if I can draw this. If N1 is this is N1, this is a normal vector to the red plane, and then I've got the blue, I've got a normal vector to the blue plane. Let me start them at the same point where they intersect. Then I am going to get a purple vector, N vector, that's perpendicular to both that and that. So it's kind of coming out of the board at you. All right, but anyway, so I can let N vector be this cross product of these other two. That's going to give me a perpendicular one. And then I can just, if that's ABC, then I can set it equal to what this vector is and plug that into my equation and use that point of intersection. Okay, so hopefully that makes sense. Much easier way to do that. And then the last thing, and I'm going to let you go because I know I didn't keep you longer, but anyway, so volume of a parallelepiped head. Did you read through that? I know you're talking about it yesterday. So parallelepiped head has a whole bunch of, so we've got 3 vectors here. And let me just, so what these end up doing is making, you know, a three-dimensional deal. All right. All right, I'm gonna, anyway. And then what do we have? The volume of a parallelepiped head. I kind of went through this, so I'm running out of time today because I do need to get going. But on page 882, they kind of have a nice thing there. We're going to step through that. We're going to step through how they come up with it, but the volume of the parallelepiped head, which I didn't do very good colors here because I should have been up here too. Anyway. How's that? That looks a little better, doesn't it? All right. Anyway, the volume is going to equal the absolute value of A vector cross B vector and then dot C vector. So pretty simple formula. And so we'll kind of look through that in a little more detail next time, but at least you're going to be able to use it to come up